Okay, ladies and gentlemen, let's talk about buffers real quickly. Starting off with common ion effect. What is the common ion effect? Usually, we're thinking about having a weak electrolyte dissolved in pure water. So we say something like our acetic acid. Oops, sorry, I'm going to do it this way. Something like my acetic acid dissolves in water, and we're going to get hydronium plus acetate, right? And if we did our ice, we would say, okay, let's say we start off with 0.2 molar acetic acid. We'd go 0.2 minus X, and these guys both start off as zeros. So this is 0.2 minus X, X, and X. And we'd say that our Ka, which is equal to 1.8 times 10 to the minus 5 for acetic acid, is equal to X squared over 0.2, if we assume that X is much, much smaller than 0.2, and that's what we would do. Now, the difference with a common ion, we're not assuming that we have pure water when we have a common ion problem. So it would be something like you have 0.2 molar acetic acid, CH3COOH, sorry, I dropped that C, now in 0.05 molar sodium acetate. So that's how a common ion question would be stated. And how does that change things? Well, you no longer start off with zeros across the board on your product side. So I'd start up here with 0.20, but now I have 0.5 sodium acetate, which means that this is going to be 0.05 there. This is going to be 0 minus X, 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 0.2 minus X, X, 0.05 minus X. We're still going to make the assumption that X is much, much smaller. And so we get my Ka, which is equal to 1.8 times 10 to the minus fifth, is equal to X times 0.05, because we assumed X is much, much smaller, divided by 0.2. And we can solve for our X, and we can get our hydronium. Now, just think about what this means. I am already putting something here, so what's that going to do to my equilibrium? It's going to shift my equilibrium in this direction, which means it should reduce the ionization of my weak electrolyte. And that's what the common ion effect is that your percent ionization is going to be decreased by the addition of a common ion. Okay, and it doesn't have to be this, it could be this. For instance, I could put 0.2 molar acetic acid in, how about 0.05 HCl solution? And what will that do? It will once again drive my equilibrium this way and change my calculations. But you just follow ice where you put in your common ion up here in the initial. All right? Good. So that would be common ion. Now let's talk specifically about buffers. All right. Buffers. What is a buffer? A buffer is a weak acid plus its conjugate, or a weak base plus its conjugate. So remember, let's drop it an H here. Good. Plus its conjugate. It has to be a weak acid or a weak base, so that throws out anything like HCl plus Cl minus. No, that is not a buffer. But HCN plus sodium cyanide, for instance, or ammonium chloride plus ammonia, those are all buffer solutions. Got it? Now watch out. There's a way that you can they can make a buffer solution. For instance, let's say I start off with HCN and I have 0.1 molar, and they say we're going to add. Let's say I have 5 moles of HCN, and then they say we're going to add some sodium hydroxide, and we're going to add 1 mole of sodium hydroxide. Well, what's going to happen if I add 1 mole of sodium hydroxide to my hydrocyanic acid? I'm going to get what? I'm going to get water and cyanide. And how much cyanide am I going to form? 1 mole. How much cyanic acid do I have? I started off with 5 minus 1 mole. 1 mole. I have 4 moles. So guess what I've just created? I have 4 moles of HCN and I have 1 mole of cyanide. What's that look like to you guys? It looks like a buffer solution to me. So watch out. They may have you create a buffer solution without you actually realizing that that's what you're doing. So that's what buffer solutions are. Let's go with our calculations. Um, you could use ice, or I just remember Henderson-Hasselbalch, or roughly an equivalent. Here are my two favorite. Concentration of, and this is 4 buffers. This is 4 buffers. All right. The concentration of my hydronium equals Ka, concentration of my weak acid, over the concentration of my conjugate base. Now, since they are in same solution, then quite many times we can look at this as being equal to Ka moles of the weak acid over moles of your conjugate base. Because they both have the same volume, the volumes will cancel out. Now, the Henderson-Hasselbalch is if we take the negative log of all these things, and we get pH equals pKa plus the log, and these flip now. Concentration of your concentration of your A minus over concentration of your weak acid. And those are the two equations I use. You can use, if you have a base buffer, then it's just going to be flipped. Hydroxide equals Kb times the concentration of your weak base over the concentration of your conjugate acid. Once again, those can be mole over mole, and then POH equals PKB plus the log of your conjugate acid over your weak base. All right, so those are the two calculations we do. Ideal buffer. The ideal buffer is when your concentration of your weak acid equals the concentration of your conjugate base. And so what does that mean? That means my pH equals my pKa. So that's a perfect buffer. POH equals my pKb. That's a perfect buffer. Or this other equation, it would say that that's when my hydronium equals my what? My hydronium concentration equals my Ka. So those all represent ideal buffer solutions, right? Capacity. Capacity means how much acid or base can I add before I start having a drastic impact on my pH. And capacity is just based upon the concentration of your weak acid and the concentration of your conjugate base. If I have 5 molar HCN and 5 molar CN minus versus 0.1 molar HCN and 0.1 molar CN minus, this has a much greater capacity. It can handle the addition of much more strong acid and base. Good. And then range, let's clean this up a little bit. Magic. Where's my magic? Ooh, under magic. Here's magic. Ooh, abracadabra. Ah, great. Range. Range is simple. My typical range is my ideal plus or minus 1 pH unit. And so that would be usually what? pKa plus or minus 1 pH unit. All right? It's assuming that we are dealing with a acid. If you're looking at a base buffer, then you're going to have what? POH plus or minus 1 unit. And then finally, addition of strong acid, strong base. This is only qualitative now. You no longer have to do this calculation, is what I'm told. And so what I'm going to do is go back to this. We know that hydronium is equal to the Ka times the concentration of my weak acid over the concentration of my conjugate base. So if I start off with my weak acid and I'm going to add hydroxide, and what am I going to get over here? I'm going to get water plus A minus, right? So depending on how much this is going to be, regardless of how much OH I have, this is going to be a minus X and this is going to be a plus X. So if I am adding, so if we add a base, what's going to happen? This number is going to go up. This number is going to go down. What's going to then happen to my hydronium concentration? Well, denominator up, numerator down, this number goes down. And so what would I predict would happen to my pH? So my pH is going to go up, right? So the addition of my hydroxide will cause my pH to go up. And the reverse effect, if I'm adding an acid, right, I have my conjugate, and it's going to be a reaction where my conjugate is going to be converted into my weak acid. And so this value is going to go down. It's going to be minus X, and this is going to be a plus X. And so what's going to happen? This is going to go up. This is going to go down, which means this is going to go up, which means my pH is going to go down. Whew, okay, really, that is all you need to know about buffer solutions. And then this will play into what we have to do next time with titrations. I hope this is enough for you to understand, and I didn't go too quickly. Bye-bye.